this video, we're going to look at how to use algebraic methods to find limits. So what are we going to do here? Well, first of all, why would we use algebraic techniques for finding limits? Well, there's certain situations in which this can be helpful. And those situations are, in specific, a couple of different ones to begin with. This first one here, if you have that the limit as x goes to a of f of x is not equal to the value of the function f at a, but f of a is defined and the limit as x goes to a of f of x exists, just like in this picture here. So as we can see, the limit exists as we get close to x is a from both sides of a. Limit seems to be L, but yet the limit of the function is not equal to the actual value of the function indicated by the blue dot right above. So algebraic techniques can be helpful in this situation. Also, in a situation like this, in which the limit of the function f of x as x approaches a exists, but the function is undefined at a. So the picture, like we see here, right? Basically the same picture as in the previous one, except the function's not defined here at x is a, but as x approaches a from both the left and the right, the limit does exist. So basically we're talking about situations in which we have a removable discontinuity. So what we're going to do now is say, well, let's look at a couple of examples, get some general strategies going about how we could use algebraic techniques to find such limits, and then hopefully that'll be good enough to give you an idea to do some on your own. So let's talk about this first example here. First example, let's use algebraic techniques to find this limit right here. Limit as x goes to -1 of the rational function, which is the ratio of 2x squared plus 3x plus 1 divided by x squared minus 2x minus 3. Now, first thing we want to note is we have our rules from previous video that if we have a rational function, and as long as the denominator is non-zero at the value of x that it's approaching, in this case -1, then we simply evaluate the function at that value of x and obtain the limit. But notice here, if I plug in x is -1, so the question is, what happens when x equals -1? Because if everything is non-zero in the denominator, then we can go about our business. Well, if I plug it in, what do we get? Well, plug it in. 2 times a -1 squared plus a 3 times a -1 plus a 1 in the numerator, all divided by -1 squared minus 2 times -1 minus 3. So what do we get? That's 2 minus 3 plus 1 in the numerator, and in the denominator, a 1 plus 3 minus 3. Notice that here we get 0 over 0. And of course, that is undefined, and more specifically, the denominator is non-zero, so we can't just simply plug in the value of x here. Now, later on in the calculus discussion, we're going to see that this 0 divided by 0 is a special situation. And in fact, when we have 0 over 0, we call that an indeterminate form. And what it means is that this limit might exist. We just don't know. Think of it as it's not determined yet. It's indeterminate. And so might exist, this limit, might not. And so we got to do other things. So we try to think about, okay, if this limit exists, clearly the function is not going to be defined at x is -1, but that's okay, because it could be that situation in which we have the removable discontinuity in the graph, in which there's, say, like a hole in the graph at x is -1, but yet the limit still exists. And in this case, we have a rational function. And so perhaps there may be a common factor in the numerator and denominator of this limit for which could, quote unquote, be removed. So when we see ratios of polynomials or rational functions and we get one of these indeterminate forms, as we say, it's worthwhile to attempt to factor the numerator and denominator and see if there is a removable factor. So let's try that. So what are we going to do here? We're going to try to find this limit as x goes to -1 of 2x squared plus 3x plus 1, all divided by x squared minus 2x minus 3. And so because I have not yet evaluated the limit, I'm just going to rewrite the limit. Now it's important, this notation here, we don't take off the limit notation until we actually evaluate the limit. I'm just rewriting the limit right now. So this limit as x goes to -1 of this ratio is the same as this other limit. And again, we're going to attempt to factor the numerator and denominator. So they're both quadratics, should be able to be factored. The denominator is the easier of the two. Notice that's just a x minus a 3 times an x plus a 1. Kind of reverse FOIL, if you will. And in the numerator, we know we're going to have a 2x, we're going to have an x, and then it's got to have a plus 1 and a plus 1 to work out. So the first limit is equal to the next limit, the second one, right? Those two limits are the same. And notice that indeed the x plus 1 is a factor that is appearing in the numerator and denominator, which can be removed because, of course, since we're only taking the limit, then we don't necessarily need to be defined at x is -1, and that's what allows us to remove the common factor. So this is the same as the limit as x goes to -1 of 2x plus 1 over x minus 3. And now that problem spot of the factor of x plus 1 in the denominator has been removed. And so I can take the limit, and now I have a rational function for which is defined at x is -1. So I get a 2 times a -1 plus a 1 in the numerator, and a -1 minus a 3 in the denominator, giving me -2 plus 1 on top, -4 on bottom. What do we get? That is a -1 over -4, which is a 1/4. So in this case, the limit does exist, and even though the function itself, this rational function here, is not defined at x is -1, the limit still exists at that location of x is -1. So we should expect a hole in the graph at that location, and in fact here is the graph of that function that we were just investigating. Notice that right over here is the location of x is -1, and the limit exists, but yet the function is not defined there. And that is all consistent with the algebraic technique that we just performed. So one technique you might want to keep in mind when trying to find limits that are of indeterminate form of the form 0 over 0 is, if possible, can you factor? And if so, try it. All right, we have another example to look at here, and that is this other example. Let's use algebraic techniques to now find this limit. Limit as x goes to -4 of the function, the ratio square root of x squared plus 9 inside the root minus the 5 on the outside, all divided by x plus 4. So here we have combinations of functions, right? We have roots of quadratics, we have a linear function in the denominator, and it's worth to note that at x is equal to -4, what happens if I plug that into the function? I'm going to get square root of -4 squared plus a 9 inside the root minus a 5 on the outside, all divided by -4 plus a 4. And notice that's the same thing as the square root of 16 plus 9 is a 25 inside the root minus a 5 on the outside over 0. Of course, square root 25 is 5. 5 minus 5 is 0 over 0. So again, we get this indeterminate form, and we should be thinking, maybe the limit actually does exist there, even though this function is not defined at x is equal to -4. Now, unlike the previous example, we do not have a rational function here, so we can't just simply try to factor the ratio of the polynomials. Instead, we have combinations, right? Like I said, we have a square root function. Inside the square root is a quadratic, and then this constant on the outside in the numerator, and then there's that linear function in the denominator. So we think, what kind of algebraic techniques might help here? And remember, another technique that we can do to not change the actual function is by multiplying by various forms of 1, right? The same number divided by the same number. Non-zero number, that is. So that root is kind of calling out for this, and that is perhaps something algebraically nice might happen if I multiplied by 1 of a special form, and that special form here is to try to use the conjugate of the numerator. So that's what I'm going to attempt to do. Let's take a look. Limit as x goes to -4 of all this stuff, the square root of x squared plus 9 minus a 5, all divided by x plus 4. Well, now I'm going to multiply, again, by the conjugate of the numerator. So remember, if you have a root of some stuff and then plus or minus some constant, the conjugate of that is just going to be the same exact expression, except change the signs in between the two different terms. So notice I'm multiplying by square root of x squared plus 9 in the root plus a 5 on the outside. And because I'm multiplying by 1, I must do that on the top and bottom so that I'm not actually changing the function I'm taking the limit of. So what happens here when I do that? Let's see. Well, let's do a little more algebra. This is the same as the limit as x goes to -4. Okay, on the numerator there, if you multiply out those two expressions, it's like a difference of squares, right? We got the square root of x squared plus 9 times itself, right? So squared, and then minus 5 times 5, so minus 5 squared. So in fact, what we're going to be left with is an x squared plus a 9, and then minus a 25, right? Square root x squared plus 9 squared minus 5 squared. And in the denominator, there's this big old mess of stuff, but I'm just going to leave it as the product, not multiplied out, because there's really no reason to multiply it out right now. Kind of think of it as why multiply unless you really have to. So what happens next? Well, let's combine some terms in the numerator here. We get limit as x goes to -4. Okay, x squared plus 9 minus 25 is x squared minus 16 in the numerator, all over x plus 4 times the square root of x squared plus 9 plus 5, that whole quantity. And then notice x squared minus 16 is another difference of squares that we can actually go ahead and factor. And so that's what I'm going to do. Limit x goes to -4. All right, x squared minus 16 factors to x minus 4 times the x plus 4. And in the denominator, still we got x plus 4 times the quantity square root x squared plus 9 plus a 25. And so, again, we see a common factor occurring. In this case, x plus 4, so that's indicating some removable discontinuity in the graph. And what I'm left with is just the limit as x goes to -4 of x minus 4 in the numerator, and then the square root of x squared plus 9 plus that 5. We had a 5 on the previous part, right? Plus the 5 on the bottom. So now the denominator is not going to go to 0. Let's go ahead and take this limit. In the numerator, we get a -4 minus a 4, all divided by square root of -4 squared plus a 9, and then plus a 5 on the outside. So what does that give us? -8 in the numerator. And then the square root of negative 4 squared plus 9, so that's square root of 16 plus 9, which is square root of 25, which is 5. So we get a 5 plus a 5 in the denominator. What's that? Negative 8 over 10, which is a negative 4/5. So, here you go. Another technique, multiplying by 1. In this case, we multiply by 1 of the form conjugate of the numerator, top and bottom. And it allowed us to do a little bit of algebra to rewrite it, remove a common factor, and then actually take the limit. If we look at the graph of this function, here it is. There's the location of x is negative 4. And notice right there the removable discontinuity right at the ordered pair, negative 4 comma negative 4/5. So it's just a couple of examples to get you going, right? Use your algebra. There's various things that we could do. Factor if possible. Multiply by 1 if possible. Combine like terms. Find a common denominator, right? There's a lot of different things that we can do, and in this video is just showing a couple of examples showing that this can be done in situations where there's removable discontinuities. Sometimes the algebra is straightforward. Sometimes you got to do a little bit of work. But in general, that is it for this video. And until the next video on limits, math and beats, I'm out.